Today we're going to look at a simple projectile motion problem. Let's start, let's just say we have a cannon. Here's our little cannon, and it fires a cannonball with an initial velocity of 50 meters per second, and it's set up at an angle of 30 degrees to the ground. From these two pieces of information, we can find out everything that we could possibly want to know about the path of this cannonball. So if we simplify our scenario just a little bit, and any type of projectile motion problem we can simplify here, we're going to have an initial velocity, again as we said, of 50 meters per second at an angle of 30 degrees, and realize that we draw this initial vector, but the instant at which the projectile is fired, the velocity begins to change because the y component is continuously changing, and so the overall velocity of this projectile is changing. And if we break it down and we look at our components, we realize that there's a y component and there's an x component. And as we've said before, these two components act independently. This x component is uniform. That means it does not change. While our y component is constantly changing with an acceleration that's equal to the acceleration due to gravity. And so our path is just going to look something like that, a parabola. We can figure out what each of these initial velocities are using our trigonomic functions. So our y component, that's the opposite side, so we're going to use sine. So sine theta times the initial velocity, which is equal to sine of 30 times 50 meters per second. And you're just going to have to trust that's what it says. And if we calculate that through, we get an initial y component of 25 meters per second. If we do the same thing for our x component is adjacent, so we're going to use cosine theta times the initial velocity. So we have cosine of 30 times 50 meters per second equals, and that gives us a an x component of 43.3 meters per second. Now with these two, we can find out everything else. If we realize again then that our path of the projectile is parabolic, yeah, that's pretty good, we can view it as two halves of a whole. And in these two halves, we know that the time for the first half is going to equal the time for the second half, and we know that if we find those two halves, we can then find the entire time. We can find the time for the first half by understanding that the velocity in the y direction at the peak is 0 meters per second. Remember, it's slowing down because of the acceleration of gravity. Okay, AY is equal to G. Let's call down negative, so we'll say it's negative 9.8 meters per second. Squared. And with this, using our accelerated motion equations, we can figure out both the time to that peak and how high that peak is. And so let's start with using VF equals VI plus AT. And here our final velocity again is 0. Let's actually rearrange it first. VF minus VI divided by the acceleration is going to give us our time. And remember, this is just half of the time. Our final velocity is 0. Our initial velocity again is 25. And our acceleration is negative 9.8. And this gives us a time to the peak of positive 2.55 seconds. And again, we're worried about these signs a little bit, because if you ever get a time that's negative, you know you've got a sign error somewhere. So kind of keep that in mind. Use that as a gauge. So our time to the peak is 2.55, which means that our time from the peak is also 2.55. So that means our total time is 5.1 seconds. And then with this, we can also calculate the maximum height at which the ball reaches. Okay, knowing that the time to the peak is 2.55 seconds, and the acceleration is negative 9.8 meters per second squared, and the initial velocity is 25 meters per second, and the final velocity is 0. So here we're going to use another one of our accelerated motion equations, s equals ut plus 1/2 at squared, where s is the height, u is the initial velocity, of course t is our time, and a is our acceleration. So if we plug these in, 25 times 2.55 plus 1/2 times negative 9.8, and we're going to come down here a little bit, 2.55 squared. And if we work that all out, keeping in mind that this expression right here is going to give us a negative value, so we end up with 63.75 minus 31.86, and we get a height of 31.89 meters. So that's how high it is to the peak. That's the maximum displacement in the y direction. Then the last thing that we're going to use all of this information for is to find the distance. And the distance it travels is the x component, the total x component or distance in the x direction. Here, remember we said that our x component of the velocity was uniform, so we can use our only uniform velocity equation, which is v equals d over t. And we're going to rearrange this a little bit. Dx equals vx times t. And way back there, we remember that our x component of the velocity was 43.3 meters per second. Our total time is 5.1 seconds, and this gives us a total distance that the cannonball traveled as 220.69 meters total distance.